Dimensional tiering is the type of scaling that doesn't ignore the differences between dimensional quantities. Or in other words, to dimensionally tier something is to take into account how many dimensions the thing occupies. So for example, if a character destroyed a tesseract, also known as a hypercube, using dimensional tiering, this would be a fourth dimensional feat, since tesseracts or hypercubes are defined by being fourth dimensional. So why does this difference matter? Well, let me give you an example to show you how important this difference is. Let's take a square with a length and a width of 1 unit. This square is a true two-dimensional object, and thus has absolutely no height at all. And if we compare it to a cube with at least 1 in length, width, and height, how many squares could we fit into the cube? Well, the square has no height or 0 height, so even an infinite amount of squares stacked on top of each other still wouldn't make a cube. So to ignore dimensionality is to ignore just how many squares the cube can fit within it. This is the same problem of how many zeros are needed to be added together to reach 1.
Sets are mathematical objects that contain other objects. This is a set, specifically one that contains nothing. It's completely empty. We can then define 0 as the number of things contained in this particular set. More technically, we prefer to use the term cardinality. Similarly, we can define 1 as the cardinality of this set, 2 as the cardinality of this set, and so on. But what if we put all the natural numbers into a single set? There's nothing about the definition of a set that forbids never-ending sets like this. Notice how this gives us a nice definition for infinity. If regular numbers are the cardinalities of sets with corresponding numbers of objects, then infinity is the cardinality of a set with a never-ending quantity of objects. We know there's many different finite cardinalities, but then are there many different infinite cardinalities, or is there just one? To find out if this is the case, we need a way of telling whether two sets have the same cardinality, then figure out if it's possible to have two infinite sets with different cardinalities. Notice that if two sets have the same finite cardinality, it's possible to pair each element in the first set with its own personal and unique element in the second set. It's also possible to do this the other way around. If the sets have different cardinalities, you can't pair things up uniquely, resulting in complicated love triangles. This is antithetical to many mathematicians' desires to avoid convoluted social situations, and is thus contrary to the definition of sets with equal cardinalities. Notice that there's nothing stopping us from trying this property out on infinite sets. Even though there are infinite odd and infinite even numbers, we can define a pairing between them. It's pretty straightforward to prove that everyone here is uniquely paired up. So they must have equal cardinality, meaning there's just as many even numbers as odd numbers. Makes sense. But here's where it gets weird. You can do the same thing between the even numbers and all of the integers. The conversion process is simply to multiply or divide the original number by 2. Every even number is paired up with a unique integer, and every integer is paired up with a unique even number. And this is why infinity is so confusing. People will often tell you that there are as many even numbers as there are integers. We use this language because it was the clear language to use when we were talking about finite sets, even though it doesn't necessarily make intuitive sense in the infinite case. Using language like this is like saying we're illuminating a surface with a negative light source. It's like saying the average family has 2.19 children. None of these terms make consistent sense, and they're not supposed to. We continue to use the language of the simpler definition when applying it to new cases. But when we teach people about infinity and use these phrases without noting this, we create the false impression that there's supposed to be some kind of intuitive notion of size that works on infinities. The size of an infinite set is an abstract concept, completely divorced from its usage as a term in English. That's why I'm going to continue to refer to this property we're talking about as cardinality instead of size, in the hopes that it helps emphasize that this concept doesn't really work the way the nomenclature of size would suggest. So far, it's looking like it might be the case that there's only one infinite cardinality. It kind of makes sense, too. If infinity is already bigger than all the other numbers, how can there be something even bigger? To confirm this, let's keep trying to make an infinite set that has a different cardinality than the set of all numbers. To start, it turns out that the rational numbers have the same cardinality as the integers. First, consider only positive rational numbers. We can order them by starting at 1 over 1, then going to 2 over 1 and 1 over 2, then going to 3 over 1, 2 over 2, and 1 over 3, followed by 4 over 1, 3 over 2, 2 over 3, and 1 over 4. Of course, we're going to end up with some duplicate numbers this way, but we can simply skip over those. This process is a way of matching up any positive rational number to a natural number. By giving a way to put every rational number in a single file order, we give each rational a corresponding natural and vice versa. We can extend this procedure to match up 0 and the negative rationals by simply mapping 0 to 0 and the negative integers to their corresponding negative rationals. Because we can convert between rationals and integers, there are as many rationals as there are integers. If you haven't heard this before, you may find it surprising. Our intuition of size tells us that making all the combinations of elements in a particular set should result in a much bigger set. But since we're unconstrained by intuitive notions of size, we find that it's actually possible to pair up an infinite set of items with an infinite set of pairs of those items. If making this bigger set resulted in the same infinite cardinality, maybe no matter what we try, we'll always end up with the same infinite cardinality. So let's try one more thing. Let's try making a single file sequence of all the real numbers. Our first idea might just be to try writing out all the real numbers in order. But then, which number comes after 0? Is it maybe 0.1? But then we've already skipped over a bunch of other numbers. No matter how small we pick the second real to be, there's always something in between, so we'll always skip over something. So trying to write everything in order will not work. We also can't use the trick we use to sort out all the rational numbers, because that would skip over irrational numbers like pi. There's other things we could try to make a list of all real numbers, but none of them seem to work. It doesn't seem to be possible to make a list of all the real numbers, such that every real number gets its own integer number spot on the list. At this point, we should stop trying to prove that we can make such a thing, and start trying to prove that we cannot. An intuitive justification for going down this route is that integers only have a finite number of digits, but all real numbers have infinite numbers of digits. It's impossible to use a finite amount of information to accurately represent an infinite amount of information, so you can't give each real number its own integer. To make a more formal argument, we can construct a proof by contradiction, where we prove that the concept of a complete list of all real numbers contradicts itself. This proof is called Cantor's diagonalization argument, and its generalized version will be helpful to us later. The fact that we can't make a list of all the real numbers finally tells us that there's actually more than one infinite cardinality, so we can't just slap the symbol on these sets and call it a day. Since all the Greek and Roman letters are busy doing physics or whatever, mathematicians invoke the use of Hebrew letters. Specifically, the cardinality of the integers, which is also the cardinality of the naturals and the rationals, is denoted bet 0, while the cardinality of the reals is denoted bet 1. If you've heard about this topic before, you might be wondering where Aleph went. They don't break right now, but we'll get into their story once we explore these cardinalities a bit more. I'd like to point out that not only are these cardinalities different, but bet 1 is in some sense bigger than bet 0. Just like before, we can make a general definition of what this means that works on both finite and infinite sets. If we have a set with 5 elements and a set with 4, notice how it's impossible to give each of the original elements its own unique element in the corresponding set. This means the first set is larger than the second. Notice how this definition is the opposite of sets having equal cardinality. The set has greater cardinality than another one if we cannot make a unique pairing between their elements. So now we've seen that not only are there many different infinite cardinalities, but some of them are actually bigger than others. This system of cardinalities is called the cardinal numbers. This name suggests we can do arithmetic to add and multiply cardinal numbers, which is exactly what we're about to do. Just like our definition of cardinality, we want our definition of arithmetic to produce the results we expect when we use them on finite numbers, while keeping them general enough to work on infinite numbers as well. For example, consider this sum. Notice that 5 is also the number of elements we get if we combine a set with 2 elements and a set with 3 elements. In this way, we can define what it means to add cardinalities by defining something to do on the sets those cardinalities describe. Using this definition, we get an operation that behaves exactly like conventional arithmetic addition for finite numbers, but we can apply it to infinite numbers as well. For example, we can find the value of bet 0 plus 1 by finding the cardinality of the natural numbers with 0 thrown in. The result afterwards is just the non-negative integers, which also has cardinality bet 0. So bet 0 plus 1 is bet 0. Similarly, we find that bet 0 plus bet 0 is still bet 0, because combining the even and odd numbers gives us the natural numbers. Finally, bet 0 plus bet 1 is like combining the rationals with the irrationals to get the real numbers, so we get bet 1. Now, we can define subtraction as the operation that undoes addition. But this is a bit tricky. As we've seen, bet 0 plus 1 is bet 0, but bet 0 plus itself is also bet 0. That means bet 0 minus itself could be 1, or it could be bet 0, or it could be any number of things. But you've probably seen something like this before in the form of square roots. Remember that the square root of 4 is not just 2, but also negative 2. We simply acknowledge that the expression in question refers to multiple values, and make sure not to treat it as if it is unique.
Multiplication is defined as the cardinality of a set containing all pairings of elements from the first and second sets. So 2 times 3 is 6. Interestingly, bet 0 times itself is still just bet 0. Similar to what we did with the rational numbers, there are as many pairs of natural numbers as there are natural numbers themselves. Bet 1 times itself is also bet 1. Every pair of real numbers can be assigned its own unique real number and vice versa, so the two sets must have equal cardinalities. You can perform this assignment by taking any pair and interleaving their digits to get a single real number. Deinterleaving lets you go the other way, assigning real numbers to pairs. Finally, raising 2 to the power.
So we're going to talk about space-filling curves. So already that sounds sort of counterintuitive. Like a curve is like it's a very skinny one-dimensional thing, but space is like two-dimensional or something. So how can you have a curve that fills up everything in space? So we're going to build a curve starting with something very simple, and then we're going to sort of change it. So let's start with this curve here. So this is 3 sides of a square. So at the moment, this is really not very space filling, right? It's just 3 lines. So we need to kind of make it more squiggly, and we'll get there. So let's draw a grid on this. So like 4 squares. And so my curve is like going through the centers of those squares. So what we're going to do to make this red curve more squiggly is divide each of these squares into 4. So like chop it up. We want to make a more squiggly version of this, but we're going to use the same shape. So here's how you do it. You sort of have to rotate it a little bit to make it work. So there's the same shape that I've rotated it. And then we'll do one like that, another one like that, and one like this. And then we need to connect them up. So let's connect them up like this, and like this, and like this. And you can see this is maybe slightly more space filling, like it's getting more places than this one was. And it's sort of made of the same stuff. So, well, let's do another one. Why not? And then in each one of these squares, I need to put this thing here. So let me make a grid. And then I just have to turn things the right way again. So I want to take this thing and rotate it and put it here. So it's going to start like that. And it's going to end like that. And in the middle, it's going to do this, and it's going to do this. And let's connect them up with red, because we've got that shape. And then this one over here, let's do this one next, because it's easy, because it's just the reflection of this one. Connect them up, boop, boop, boop. And then these, I'm going to go to this now. So this is going to be like that. Connect up, connect up, connect up. Okay. And then again, we connect up in the same way. We do of course like that, and like that, and like that. And we've got something that's more squiggly, more sort of space filling. And you can see how like you would just continue doing this. So this is the Hilbert curve. So this was invented by or discovered by David Hilbert in 1891. Really, these are like steps in the construction of it. The Hilbert curve is when you do this infinitely many times.
You're using a Sharpie, which has thickness to it,
Right.
but surely a theoretical line has no thickness.
Yeah, 0 thickness.
So if something has 0 thickness,
Right.
it's not going to fill any space.
Well, right, every step, the thing that you have has no thickness, is filling nothing. But somehow when you go infinitely far, well, actually what happens is that in a rigorous way, which I'm not going to get into, but actually what happens when you go infinitely far, this curve hits every point of the square. So somehow, at the limit, when you get infinitely far, boom, you've got everything. This construction is not just used for this sort of infinite thing. This is also a way to sort of pack sort of two-dimensional data in a one-dimensional order, right? So suppose you have a bunch of two-dimensional data that you need to store for some reason, and you need to store it in some linear order, but you also want this bit of data and this bit of data. They're quite close to each other in 2 dimensions, and you would like them to be close to each other in the ordering. And the Hilbert curve kind of gives you a way of often 2 points that are close together in 2 dimensions are also close together. A very large trash can. So final thing, this is sort of a 3-dimensional version of the 2-dimensional Hilbert curve. So this is sort of 3-dimensional versions of a lot of these. This is the 3rd step, right? So rather than showing the whole sequence sort of as an extruded animation, this is just the 3rd step of that sequence, and you get this very squiggly curve that is filling 3-dimensional space, or a 3-dimensional cube.